Mass of a proton is equal to 1.00726 U, where U stands for atomic mass unit, which is a very, very tiny unit of mass. Just like how we measure day-to-day stuff mass in kilograms, we usually measure the mass of tiny particles like protons and neutrons using this particular unit called as the atomic. This is called as atomic mass unit. Similarly, in the same terms, the mass of a neutron turns out to be 1.008664 U. Now you can see I'm using a lot of significant figures because I'm trying to explain a concept to you. Okay, now with these, I could ask you a simple question. What is the mass of a helium nucleus? What's the mass of an alpha particle? So find mass of an alpha particle, which is just the helium nucleus. Now you can Google that as well and find it out, but don't do it yet, because I want to teach you something amazing. Now you may have gone through Bohr's theory and Heisenberg's uncertainty principle, Pauli's exclusion principle, all the stuff about the quantum mechanics, and they're really fascinating stuff. But if that has not fascinated you yet, today's topic is seriously going to blow your mind away. So allow me to explain that to you using this example. I want to calculate in this episode the mass of the helium nucleus. Alright, the helium nucleus, as you can see over here, has 2 protons, that's atomic number, and it has total 4 particles, but 2 of them are protons, so the remaining 2 are neutrons. So this contains 2 protons and 2 neutrons. Therefore, the calculation of mass of the helium nucleus is pretty trivial. Since we know mass of the protons and the neutrons, we can calculate the mass of the helium nucleus. So let's do an attempt. The mass of the helium nucleus, 2He4, it's going to be, it has 2 protons, so 2 times mass of the proton, plus 2 times the mass of the neutron. And all we need to do now is crunch in the numbers in our calculators. So let me do that. And you guys can do it as well yourself. You can pause the video and just check whether everything is, all the calculations are right. So it's 7276. So this number will turn out to be 2.014552. And this number will be just 2 times the mass of the neutron. So 1008664. So that is 2.017328. And together, we just have to add them, 2.014552. And you get 4.03188. Pretty simple, huh? That's the mass of the helium-4. Okay, now what we can do is we can Google it. So now, I want you to Google the mass of the helium nucleus. Just do that. I'm going to do that over here as well. Feel free to pause the video while I do the Googling. Let's see. Okay, so here I have the mass. And if you look at the mass, this is what I'm seeing right now on my phone. That is the mass of the helium nucleus. And what is amazing is that number is not the same as this number. Something is going on. So let me just write that number down. The real mass of the helium nucleus, so I'm going to call this actual mass, or the experimental mass. We have to trust Google for that. But anyways, the experimental mass of the helium nucleus turns out to be 4.002602. And there's a sum of the error over there. We can forget about the error. And so the question is, what's going on? I mean, we thought this was to be a fairly simple problem. We knew the mass of the protons and the neutrons, yet something is not adding up. Literally. Something seriously is going on over here. But this sort of thing happens all the time in the physics world. You predict something and the experiment shows something completely different. That's okay, but we need to come up with a theory to try and explain what's going on. If the masses don't add up, we can say there are some extra particles, or maybe we haven't taken care of something, we haven't accounted for something. But the problem is, the mass is smaller than what was predicted. This is the actual mass and it is smaller. If it was bigger, we could come up with a simple idea. We could say there are some undiscovered particles in there, and maybe it's those particles which are contributing to the mass. But it is smaller. How do you factor that in? Well, all is not lost. We can still come up with a theory. A simple theory would be something like this. Look, the mass of the protons and the neutrons, which you calculate over here, maybe these are different protons and the neutrons. Maybe the protons and the neutrons inside the helium nucleus way lesser, way smaller. Well, we could check that. What you can do today is you can take a helium nucleus and you can bombard it with some high energetic particle like a proton or neutron or something you can do, and you can rip apart its neutrons and protons, and then you can experimentally measure each one of them. And guess what we find? The protons and the neutrons do weigh so much. So there's nothing wrong with the protons and the neutrons. They really weigh the same thing. There's only one kind of proton and one kind of neutron in the universe. So they weigh the same. So nothing's wrong over here. It's just that when you weigh them together inside the nucleus, as a nucleus, you get a smaller answer. So something very freaky is going on over here, and this is truly mind-boggling if you think about it, because masses are not adding up. And this difference in the mass that we get is what is called as the mass defect. Now, if you're a lazy scientist, you could say, well, okay, that's helium nucleus. Let's forget about helium. Helium is weird anyways. Helium balloons float, they defy gravity. Helium is weird. But this is something that you find not just for helium, but for every nucleus. Every nuclei we know today has the same phenomena going on. If you calculate the sum of the protons and the neutrons mass together, it always turns out to be larger than the actual mass. Mass of every nucleus is smaller than the mass of its constituent particles put together. And that is what we call as mass defect. So let me write that down. Mass of every nucleus is, and I'm gonna highlight this, is smaller. And that's important. I'm writing it big. The smaller. It's ironic, right? Anyways, I'm writing it big. Smaller than the sum of the masses of its constituent particles. Okay? We can write this mathematically. We can say mass of a general nucleus, and the way we're going to show a general nucleus is, as you can see over here, there's a name of the element. Let me call that as X. Then there's the number of protons, the atomic number. We usually call that as a Z. And then the total number of particles, protons and neutrons together, we call that as A. This number in general is going to be smaller than the sum of the masses of the protons. So what is the total mass of the proton? Well, there are Z protons, and each proton has a mass MP, so it's Z times MP, plus, how many neutrons do we have? Well, we have total A number of particles. You remove Z number of protons, the remaining is neutrons, so you have A minus Z number of neutrons multiplied by the mass of each neutron. Okay? And so if you take the difference of these two, so let me give this a shorthand notation. Let me call this as M sum. So sum stands for adding up the masses of the protons and the neutrons. So if you take the difference, this is going to be always bigger than this one. So if you take the difference of this minus M of ZXA This is what we call as delta M, and this is the idea behind mass defect. But really, people had no idea what was going on over here. I mean, think about this. If I told you that you take an apple, put it on a weighing scale, an apple weighs 200 grams maybe, I don't know. Okay, 200 grams. Okay, then you take out the apple, you take a banana, you keep it over there, that weighs 300 grams. And now you keep them together. What if the weighing scale showed you not 500, but instead 450? How would you feel about that? Individually, 200 and 300. But together, 450. Not 500. Now, of course, in reality, for apples and oranges and bananas, it doesn't work like that. But that's what's happening at a nuclear level. But it doesn't matter at what level it happens. We need to find out what's going on over there. So we need to ask ourselves, that's the ultimate question. Why does the nucleus behave so weirdly, and what's going on over here? Eventually we're going to see that the question itself, why nucleus behaves so weirdly, is the wrong question. Alright? And it took an Einstein to eventually figure out what happens over here. So we're going to talk about all that stuff in the upcoming video. So stay tuned.